Federal University of ABC.
Doesn't mean that they teach ABCs there. Just ABCs are
They're the initials of the cities that are around the university.
Oh,
Santo André, São Bernardo, and São Caetano.
all saints.
oh, that's
So
important.
that's why it's ABC.
Yes.
Anyway, so he's going to talk about the ACT constraints on low-scale inflation and the mechanism for vector dark matter production. Thank you, Gustavo. Go ahead.
Okay, so hello everyone. I'm here to talk to you about two of the results from the Atacama Cosmology Telescope that have been recently published. And what they infer for low-scale inflation, and I'm also going to present to you a mechanism for dark matter production. So first, let's talk a bit about the Atacama Cosmology Telescope. It is a telescope that is specialized in gathering data about the cosmic microwave background. And it has a very high sensitivity. It has Arc-minute resolutions in 3 frequency bands. And it has operated for 5 years. It's now not collecting data anymore, but it's still releasing what they have analyzed about this data. And one of their papers has been released last month. And these results are a little interesting. So this data release 6 has been published with combined analysis of data from the Planck Telescope, the WMAP project, DESI, BOSS, and Pentium Plus. So they use several different amounts, several different experiments to examine what they have from the CMB. And this is the paper that I'm referring to. They also have released a companion paper, which also analyzes other things about power spectrum. We're going to use data from both. I have shortened the list of collaborators. The list is actually much larger than that. But don't worry about this abstract. I'm going to give you the most important
Which
results.
date is that? What day was it submitted? Just to keep it.
I don't think the date is here, but it's
I
last
have
month.
this in the one, okay.
Yes, that's year 1. So before we move into inflation, I'm going to give you just a brief review of the most interesting, in my opinion, most interesting results from the Atacama Cosmology Telescope review, the data published. They have found that we have near scale invariance and adaptivity of the primordial perturbations. So the running of the spectral index is almost 0. Another thing they have found is that we are consistent with the standard model neutrinos. So an NF is essentially equals to 3, or almost equals to 3, this means there are basically no new species with non-zero masses or self-interactions that have been found so far. Basically, they have found everything that we already knew, but they are confirming it with much more precision. They have also consistent standard Big Bang nucleosynthesis. The helium-4 fractions what we expected already. The temperature of the CMB has been measured to be 2.698 Kelvin.
Do they really measure the temperature of the CMB? Because you need,
This is written in the abstract. I didn't pay close
it's
attention.
probably from a fifth.
Oh, yeah.
Okay.
Very old.
Okay.
It's older than you, you were not, your parents were not born yet.
Yeah, it's from Kobe, so it's because you need the monopole.
Okay.
Dragon monopole. So
I just read the abstract in the when you're
Yeah.
talking about.
it may be from a fifth.
Oh my gosh.
It may be from a fifth.
We have found a cosmological constant which is consistent with -1 or very close to -1. And they say in the paper that they have found no statistically significant preference for a departure from the baseline lambda CDM model. And models that try to increase H0 or decrease the amplitude of density fluctuations, they are disfavored over lambda CDM. In this paper, what they do essentially is try to stress test the lambda CDM to see how far can we move away from it. And they find out that overall, the lambda CDM is still a very good model, as we already know. And they put some stricter constraints, some narrower constraints on some of the parameters.
Also, I think if I remember, they also put constraints on something called early dark energy models.
I believe so, I'm not sure.
I think so, right? Yeah.
Yeah.
So they're all, this model is almost dead now.
Yes.
This is a pity because I worked with it.
Don't worry.
And we are mostly interested in, or I am mostly interested in the results that refer to inflation and what all of this will apply to inflation. So let's first give a brief review of inflation. As I hope most of you know, inflation has appeared in the very beginning of the universe when it has expanded exponentially fast. And we can reproduce this effect using a single scalar field, which we can represent using this Lagrangian here. This is a very simple and very boring Lagrangian, but it gives us all of the desired results. It's fascinating. And if we use the other Lagrangian equations, you can simply recover the equation of motion of the inflaton. This field phi, we're going to call the inflaton field. And most of the things, our results are going to depend on the potential of this field. We're going to talk about these potentials in a moment. And we can also use the Friedmann equations to derive some important equations here. Equations number 3 are going to allow us to connect the value of H to the potential to the energy scale of inflation, and also the derivative of the field can be related to the velocity of the derivative of the potential can be related to the velocity of the field. Another important thing that we also have to consider in inflation is the duration of inflation, how long it takes, or how much does it expand the universe. And this is usually given by the factor called this factor n, which is called the number of e-folds, which becomes pretty clear when we look at this equation here. So the size of the universe scale factor is going to simply be the initial size multiplied by the exponential of n, the number of e-folds. Exponential folds. It is calculated using the integral of h times dt. Now, one important thing that we desire for inflation, especially for the potential, is that it has what we call the slow growth. The slow growth means that the velocity of the field is much smaller than the potential of the field. This is necessary in order to give us what we desire for the equation of state of the fluid in that period, in order to have the exponential growth of the universe. Otherwise, we don't have exponential growth, we don't have inflation, we don't have anything. So we represent this low rho, or the properties we desire through these 2 parameters here. This is called the slow rho parameters, epsilon v and eta v. Epsilon v is essentially the slope of the potential, and the eta v is going to represent the curvature of the potential. And they need to be very small, much smaller than 1. If they're close to 1, we lose inflationary properties and we end inflation. And when we think about these low rho parameters, we can relate them to observations from the CMB throughout 2 quantities, which are the tensor to scalar ratio and the spectral index. The tensor to scalar ratio essentially represents the ratio between the amplitudes of the tensor power spectrum and the amplitude of the scalar power spectrum. And it basically gives us how powerful are our gravitational waves from that period. And our spectral index, it represents the tilt of the power spectrum. And they are related in these 2 equations. And there's one more constraint, which is the amplitude of the power spectrum scalar perturbations, which can be related to the potential of the field using this equation here. And this important constraint is going to be used, all of these constraints are going to be used when we analyze single field inflation. So now let's talk about energy scale of inflation. What do I mean by energy scale of inflation? Energy scale is the numerical value of the potential, if it has lots of energy or lower energy. And this is related to the value of H through these loops. But that way down. This is related using this equation here. So essentially they are proportional. So if H is large, inflation is high scale, and if H is low, inflation is low scale. This is interesting for us. We're going to be interested in this. I'll tell you why in a while when we experiment with the dark matter production. But when we refer to low scale inflation, most models that you see, modern papers usually talk, even if they don't mention it, about high scale inflation. So H is at the order of 10 to the 13, 14, 10 to the 12 GeV. And if we talk about values of H below 10 to the 10 GeV, we already consider it to be low scale inflation. So if we have a lower value of H, we have lower V, lower potential. And the power spectrum normalization is going to cause also the initial value of epsilon to be very, very small. So like in my numerical runs, we have something like 10 to the minus 14 starting. So this is very, very flat. is much flatter than in high-scale inflation. And this will also mean that we have a very small value for the tensor to scalar ratio. So usually low-scale inflation means we will not observe primordial gravitational waves, unfortunately, but that's the result we have. Also, from the slow roll conditions, we also infer that the initial velocity of the field is going to be very small. So essentially, what we have is a field that is starts extremely flat, and at some point it starts falling down. And at this point, we like end inflation. And this is like really, really, really flat. And the velocity starts really, really, really small. The inflaton rolls down its potential very slow. And this is what gives us the inflationary properties that we use.
Yes, remind me why we like low scale inflation,
Why what?
why we like energy scale low inflation.
We're going to see this in a while because I'm going to study a model of dark matter production, and then we will see why it is interesting for us to have low scale. For the moment, I'm just commenting on what is low scale.
Do you always need to have that flat potential for the low scale?
And even in high scale, the potential is flat, but it's not as flat as in low potential, in low scale. So the lower the scale, the flatter it becomes. But we still, this flatness here basically is represented by the slow roll
Yeah.
conditions.
And will you get the same number of folds, or will you play around with that number?
We can have between 50 and 60 folds.
Still.
Yeah, I haven't mentioned this in the previous slide, but the number of folds is expected to be between 50 and 60 or 55, 65, depending on the book you've been reading.
Do you know a lower bound for this scale of inflation? Like what is the lowest it could be?
I have been experimenting with values down to 10 to the 3 GeV, but I could get even lower if I wanted. I'll show you a plot later that shows how this is possible. And one of the interesting consequences for us in low scale inflation is the difference between the initial velocity and the final velocity of the field, which can be seen in this plot. So the blue line represents high scale inflation. We start at a certain velocity of the field, and this velocity becomes more negative as time passes. And the difference between the initial and final value is about less than 2 orders of magnitude. Plus, for low scale inflation, which I have used here 10 to the 7, this difference is up to 5 orders of magnitude. So the final velocity of the field is much, much higher than the initial velocity in low scale inflation. This is an interesting result, which is going to interest us in 15 minutes, maybe less. So keep that in mind, that the difference in the velocities is very, very large. Now, before I go back to talking about the ACT results, I'm going to show you this plot that most of you have seen hundreds of times, which is an essential result from Planck telescope. It's a paper from 2018, and it basically shows me what are the primordial fields and the tensor to scalar ratio allow values from the observations. You see that the primordial field must be between 0.96, 0.97, and the tensor to scalar ratio must be very small, like below 0.1 or 0.05. And here we have some of the potentials being analyzed. So we have different potentials for the inflaton, and a few of them are going to be more favored than others. One important thing here that we can observe is that for the low scale inflation, I automatically am going to have very low value for the tensor to scalar ratio. So consequently, models like the natural inflation and hilltop quark, which drag this curve down here, they're going to show us a spectral tip that is out of the possible allowed parameter range. So these two models, for example, are not viable in low scale. In high scale, we can use them, but in low scale, they're not consistent with the observations. And we also see that these results, for example, they prefer concave models instead of convex potentials. And we also notice here that the Starobinsky potential, which is this R squared here, is pretty much inside the allowed range. It is one special case of the alpha attractors, which are represented by this yellow line here. And Starobinsky is well positioned here. This is going to change the ACT results. So let's talk about these ACT results and what they mean for inflation now. one of the first things they mention is about the scale invariance of the scalar perturbations. As I have mentioned, we noticed that the running of the spectral index is very small. They have calculated the spectral index NS to be slightly larger than we already had in Planck. So here we have, where is this? Here. The yellow lines are going to be representing Planck. The blue line is the combination of Planck and ACT, and the purple line is also in combination with DESI year one, the observations from barrier and acoustic oscillations. And we are interested in the comparison between the yellow line and the purple line, essentially, because the purple line.
See there,
Yes.
this is actually a very important point. Do you know if they use the VAO scale of DESI or the full shape reconstruction?
I don't know.
Because the VAO doesn't give relation when they give the mega matter.
I don't know. I don't know the specifics of the analysis.
Actually, I have to look this up, sorry.
They mentioned that they combine all this data in order to produce new data and data that is more trustworthy and such. But I don't know exactly what kinds of
So come up when you present the NS combined with DESI, we will be able to see.
okay.
And
Yes.
why don't you have the results here just for ACT? Is there any hidden tension?
Yeah,
or-
some of the graphics, you see that they do show results from ACT, like this blue line, for example, and this blue region, for example. In this specific plot, they haven't shown. I'm not sure why.
Okay, but everything's fine here. There's no tension.
No, there's no tension. They just find the value of NS is slightly larger, only a little bit more positive, more closer to one. They also compare the vanishing of the vanishing running of the spectral index. So TNS, DLNK is very, very small, 0.0062. Plus minus 0.0052. But the small difference here between this and the results from Planck is that this data is going to prefer slightly positive running, whilst the Planck one has slightly negative one, as can be seen here. The Planck data is slightly to the left,
Yes.
and the purple one is slightly to the right. And this can be seen in this plot. This is a reconstruction of the power spectrum. And using all of those sets of data. Let's start looking at the Planck first, which is the yellow lines. The central line is the mean value of NS, and the side lines are just going to be the confidence interval. And it is all very consistent with the prediction for the lambda CMB, which is the black dashed line, which has zero running of the spectral index. In this case, we see a slightly negative curvature, which represents the slightly negative running of the spectral index. Then we combine with the data from the ACT. The data has been collected only in a certain range of meta, which are these solid lines, and the dashed lines are extrapolations of this data. And then we have the combination of data in the case of the purple region. And we see that purple region presents a positive curvature, which is, again, the slightly positive running spectrum. But they are all very consistent with the predictions from the CMB. So this is what we have for the spectral index. Now, for tensor modes, there are constraints for inflation models. In order to measure tensor modes, we need to measure what we call the B modes, which is some sort of polarization of the CMB. And this have been measured by an experiment called BICEP-CAC. So they combine data from the B modes from BICEP-CAC in order to calculate the value of the tensor to scalar ratio. They find it to be similar to what we had before, very high confidence interval. Again, very small value of R, so we are not observing gravitation from our gravitational waves at the moment. And now, when we talk about here, they say that the higher value of NS, the same value of R, It's going to shift that allowed region and the line plot slightly to the right, and it's going to include a few models that have a slightly higher power indexes than Planck. So it's going to see this plot here. So the purple region is going to be shifted slightly to the right in comparison to Planck, and this is going to include now a few more of the monomial potentials that were not included before.
Can you go back to the image spark plane? Just
This one?
Yes, this one. So that's yellow is
This Planck.
Planck and Acton Planck is which one?
Actin Planck is the, here we have Act Planck and bicycle cap. This is all in blue. No, this is ACT. That's year one and bicycle cap. Only Planck is here, and the purple one is ACT, Planck, DESI, and
Which one is the one that does not have the SE?
does not have DESI. No, all of them have DESI.
That's the, that's the.
They all have DESI.
So, we are going to, no, actually, we must have an article out from Turn Like It will talk next week. But we've been looking for chains, they have chains in mind. It appears that it is the measurement of DESI and the mega matter that's putting the spectral index towards unity. Well, and Linda was very upset about this because he likes his Stravinsky models. It includes some others. The peculiar thing that I found very interesting is the ACT is a CME experiment, whereas DESI is not. And their main shift away from Planck is coming from DESI. This is worrying. So we would like to analyze their chains, Planck and ACT.
Without the presence of
DESI is an early experiment, and they have very different targets for different things. So the CFD being so influenced by DESI is interesting. At this point, it's just interesting to know.
Okay, continue.
Wonderful, yes, thank you.
So one of the things that we noticed that the Stravinsky model, which was previously favored, now it's not favored anymore, utilizing the sigma region here, as we can see in this corner. It was weight side, and now it's barely bordering into sigma region here with n equals 60. And I believe this also includes all of the alpha trackers, which unfortunately I have been using through all of my research. So sad. This is sad news for me.
So we sang about the alpha tracker, probably started.
He's so he's scared.
And also, we have some.
Yes.
And so we have some constraints from 2 epsilon b, which again must be very, very small, as we already expected. And the higher value of ns is going to imply that eta b needs to be closer to 0. So ns is closer to 1 and eta b must be closer to 0. And these are the results we were already discussing. And again, Planck data is in yellow, and we're most interested in the purple region, which is a combination of Planck, HT, and DESI. And bicycles. So for Stravinsky, but we need to keep it in mind. Now, I'm going to talk to you about the models of dark matter production. So if we consider a single field inflaton scenario where the inflaton is a single scalar and it possesses a shift symmetry, this shift symmetry will allow us to couple it to some U1 gauge boson modes through this Chern-Simons coupling, which is represented right here, this Chern-Simons coupling. And this is going to allow inflatons to couple to dark matter and produce dark matter. Actually, if these bosons are stable, we're going to call it dark matter. If they're not stable, we can call it a mechanism for production of standard model if they decay to standard model products. But here in this case, we are considering stable and massive bosons. And The dynamics of this background field can be derived using the Lagrange equation. The difference is going to be this source terms here. And the same thing for the evolution of the Hubble rates there. We're going to have some source term here, which depends on this coupling and the gauge modes. And for the gauge modes, we also have equations of motion. We have the modes with A0, which are, forgot the word.
Temporal.
Longitudinal.
Longitudinal?
Yeah.
Longitudinal, yes.
A0 is temporal.
Yeah, you want to read the decomposition. Longitudinal one.
Okay.
Here, A0 is the longitudinal modes, and A plus minus are the transverse modes.
It's not the time like.
And this transverse modes obey this equation of motion here. And the solution for this equation of motion will depend on the index of on the sign of this coefficient here.
Let's see it again, sorry.
See, it's fine down here. I'll talk about it. If this coefficient is purely positive, we're going to have an oscillatory solution. Now, if this is negative, and this can only be negative for one of the transverse modes, not for the other, then we can have an exponential growing solution. So we call this a tachyonic production. And here we're going to call this C, which is essentially the coupling of the field, 1 over lambda, multiplied by the velocity of the field.
Sorry. So Y is the dark matter and this vector field is just a vector radiation.
Now, phi is the photon field, and dark matter are the A0 and A plus minus.
Okay, the bosonic fields.
Bosonic fields. Yes.
Does that depend on the potential of things?
It will depend because the velocity will vary according to the potential. So the variation of C is going to depend on the potential, but the model itself not that much.
It's what's called pseudo-natural inflation.
I'm not sure.
Natural.
Use is not natural inflation.
It's not natural inflation.
No, don't get
You know, I think natural inflation is not consistent with scale. At least according to the red class.
yes.
Natural inflation is 1 minus cos phi.
Yeah, but it is not consistent for those scale.
Because of the sensor to scalar ratio.
But do you think of phi as being a Goldstone boson?
No.
Yeah, that's something not super consistent. It was trying to use the potential, but not using one reason. So this is a CPU or not CPU? It's supposed to be a super scale.
Yeah, because you didn't write the potential for the new photon in the previous slide, did you?
No, I didn't. I haven't chosen a potential yet.
Okay.
We're going to reach the potential in a moment. Right here.
Okay.
So before that, the effects of this vector dark matter prediction below the TV scale have already been discussed in another paper by other researchers. Our interest here is analyzing dark matter that is slightly more massive, with masses that are comparable to the scale of Hubble, so that's something like 0.1 or 1 or 10 times the Hubble scale. And whilst previous research was about almost negligible masses in comparison to the Hubble scale. And in order to do that study, we have first done a preliminary assumption that H is constant and C is constant. We're going to see that this has some challenges in a moment, but just for starters, we assume that H and C is constant. This allows us to have an analytical solution for the equations of motion. I'm not going to show you what it is because it's not that interesting. The interesting thing are the results. And with those results, we can find the parameter space, what are the values of C and the values of M that are going to give me 100% dark matter abundance today. So anything in these lines, each line represents one value of H at the moment of inflation. Each one of these lines, if I pick parameters below the line, we have underproduction. If I pick something above the line, we have overproduction of dark matter. and something exactly on the line is going to give you 100% of the observed dark matter today.
That's kind of a naive question.
Yes.
So I was just thinking when you showed wages for the molds, for the vector molds, that usually inflation, the vector perturbations do not grow, they decay. That's why we don't care about them. So we care about the scalar perturbations and the tensor perturbations. My
Yes.
question is whether this new field would source
I haven't considered that.
vector perturbations. Yeah, I'm just thinking, oh, okay, just thinking.
I haven't considered that.
But
Yeah.
one branch that the oscillating solution, so that will decay.
Right, but they have an exponential
The
growth.
exponential one will be the one that supplies.
So there is a vector, there could be a
Yeah,
vector,
that's a source of vector perturbation.
vector perturbation, but aren't there bounds of vector perturbations?
That's what they believe, but apparently.
I don't know, actually.
There should be, that, like, they should be.
Don't be very studying this, like, actually, now. Actually, because I think now.
Because people will say, okay, you don't care about the vector.
Yeah, usually cosmology, we simply ignore the vector
Because they
perturbations. So-
decay, there's no source, but here there is a source.
Technically, they are violation of the symmetry of isotropic industry.
Yeah.
That's how you constrain vector perturbations.
I suppose there are
You should see some incidents of some dipole, like odd modes in this technique. That's how you constrain vector perturbations.
Low multiplier?
Yes, this.
That's not denominated.
No, it's not the alignment of the optical. No, it's pure result.
So we derive this parameter space, and as you can notice, the values of H are very small if we want massive dark matter. So this is why we want low scale inflation. If we want the gauge bosons here to be massive, we need the scale of inflation to be small. Does that make sense?
Can you say it again? Sorry. How do you see this? That you need.
In order to have, for example, a mass of m equals to h, most of my values of h here are like 10 to the 9, 10 to the 8, 10 to the 7. This is low scale inflation. Okay, and you see that the more massive I want it, the lower is the scale of inflation. If I want the mass to be very, very, very small, I can have high scale inflation. So this is why we're interested in low scale inflation in this scenario, in order to produce a massive vector.
Just since I would be, how do you call it, an Indian question. No, I'll have to be polite. So when you have the low scale, so you have the very flat potential and then it drops abruptly, does that usually give you more problems with fine tuning at the end of this thing called grace layers?
It gives me
Oh, yeah.
problems with finding what, I'm sorry.
At the end of, when it drops abruptly, when you have to inflation.
Inflation ends very.
Everybody has, okay, sure. It's bad for everybody, okay. Yeah.
Our inflation ends as any other one,
Yeah.
low scale or in high scale. The difference is that the moment when we observe, the moment when we observe this drop is at the very end. This is
Yes.
very sudden. In
Yeah.
high scale, this is slightly more smooth. But
Yeah.
in low scale, this is very, very
Yes,
sudden.
right, so that one is a little bit more graceful, as they call it.
Yes,
It's not very kind.
I understand what you mean.
But they call it graceful, but it's not really, so don't worry.
Yeah, no, this behavior is complicated because I have to be very precise in the time steps of the evolution of my equation of motion. Otherwise, I lose some of the qualities of inflation. So it's slightly more painful, but it's not impossible.
So just begin to understand probably what it means that if I have that matter which is ultralight bosons, then it's high scale inflation. If I have very massive that matter, it's low scale.
Yes.
It's true, no, I think for very light as well, I think the plus for very light. like an MA, if that's what you want to look to.
Yeah, it depends on the choice of parameters.
Yeah.
It depends on the choice of parameters. So now we have to choose a model, we have to choose a potential. And we have, these are the most studied ones. I have not included the monomial ones. Simply because I didn't want to, but since I'm going to have to extend this, but you see that the choice of potentials is not exactly the biggest problem. If something doesn't work out, I can choose another. So we have this, what we call here the T&E models. Those are included in what we call the alpha attractors. Those are alpha attractors. And the Starobinsky is just the case of the E model with n equals to 1. And the hilltop quartic and natural inflation are shown here. So natural inflation, for example, already has a shift seem to include in the potential, which would make it the candidate is not for the fact that we have low scale. And here I show you what we do when we choose this potential. So first, we ask ourselves, are all inflaton potentials at low scale compatible with CMB constraints? As I have discussed here, we see that they're not. Natural inflation hilltop quartic are excluded due to the very low tensor scalar ratio, which will drag them to have much lower spectral index. Not allowed. Now, the alpha attractors remain as good candidates, at least before the release of dataset, data release 6 of ACT. And in the following results, I'm going to use the T mode with n equals 1 and HCMB as 10 to the 7. In this plot, I used to show how I choose the appropriate parameters by the initial value of the field and the alpha parameter in order to have the observed values from the CMB. So our constraint had to be obeyed. Essentially, I have one red region, which is forbidden because the tensor to scalar ratio is going to be too large. I have these two green lines here, which represent the upper and lower boundary of the spectral index. So I need my parameters to be in this line. And the purple lines, which represent different values of HCMB, they represent also the given power spectrum normalization. So I need to obey all of those constraints at once. So what I want is something out of the red region that is the intersection of those lines. When I find intersection of those lines, I have my phi in, my alpha. I can simply put those into the potential and evolve my inflaton according to the equations of motion, and I have all of the desired results.
Sorry, what is the green?
The green is the upper and lower boundary to the spectral index.
So what is alpha in the previous slide?
Alpha is just those alpha parameters, three parameters here, alpha, and also alpha here. And I have used alpha instead of F here, just a free parameter.
Got it. That's
So now let's talk about back reaction effects. When we have coupling of the inflaton with the gauge modes, this coupling might affect the inflation dynamics, and this might cause, this essentially might cause us to lose inflation, or to not inflate, or to inflate too much, or to inflate too little. We want to maintain our 60 volts. We want inflation to inflate the universe in the end.
This is like preheating, right? Because you have these modes that are growing exponentially, these vector modes.
I'm not sure if the mechanism is the same.
Like preheat.
Could be.
Yeah, when we study the inflation, then the heat, before the.
Before, yeah,
Exponentially.
exactly. It's before the inflaton gets to the bottom.
I think if the good story is after inflation, so when they are going to start oscillation, that's the big word.
But that's a little bit before. Can be before.
Yeah.
You don't need oscillation.
That's
for the inflaton to feel. I think it's fine. So it's
So
preheating.
what's
So what I do here, I analyze the behavior of the field in the presence of gauge modes and in the absence of gauge modes to see if something changes. And surprise, not much changes.
Really? So it means that you're not producing a lot of those modes, right?
Those vector,
Of the vector modes. So the vector.
yes, or at least they're not destroying
But
the.
you are.
it's still,
The density.
it's expected not to be, because of the density of the depth of the, it might expect it
Yeah,
to be much more than eventually this will compensate relation.
yes. So the divergence should cut off because the modes are growing exponentially, right?
Yes.
That's the population number basically of the modes.
Yeah, you can control that in the calculator. Because eventually, I think if you actually that like that, you don't want to produce too much.
Yeah, at some point, this growth has to be cut off, right? And not continue, correct? So,
I think the calculation we start at say the when inflation ends.
Okay.
Yeah, we stop calculation at the end of inflation. We do not consider what happens.
it's a bit different from preheating. So preheating, you have a region of resonance where you really produce a lot
Yeah,
of.
that's the activity of your company. Because if you in principle, you continue with the production.
Yes, we still need to extend the studies to what happens after inflation.
Okay.
At the moment, we are only considering inflation. Now, here, we have used the approximation of H constant and C constant as that analytical solution, calculate this. And we see that here I have only plotted phi dots, but I could also plot phi and H, and all of the values, they basically remain the same. The black lines without the presence of the H modes, and the red dots are with the presence of the H modes. There's no visible difference. So
Assuming that H is constant, it's not just set in by hand that the reaction is moved. Because basically you are saying whatever is the field wind is not altering the expansions.
I'm not sure, but assuming that H is constant is usually a good approximation for inflation.
No, it is, but like it seems like adding by hand the ingredient that there's no variation. That's my only.
Maybe. We haven't considered it. Gonna take notes into this. But what I want to say in this plot is that we have also considered C to be constant. And we have taken the final values, which was like 0.5, 3.5. But C is proportional to the velocity of the velocity of the field. I had mentioned in the beginning of this presentation that it changes by 5 orders of magnitude, which means that the initial value of C is 5 orders of magnitude smaller, which means that any back reaction present is going to be much smaller during most of the inflation. And only in the very end, we're going to reach values.
Because C, you're controlling the production is controlled by C, right?
Yes.
Like, it's the difference between the bare mass and this C times some scale. Is that what you showed in one of the slide where you show the equation for the transverse modes? So there's a region where this thing grows and a region where it does not. Yeah.
Yes.
So it's a combination of
What grows since the beginning is that there's a tachyonic window.
there's a tachyonic window. That's
Yes.
right. So it's like a preheat. It's like preheating because there's a time variation, so there is a window of resonance, let's say.
And this window is going to be pushed to the very end.
Yeah, that's okay.
Since the value of C starts very, very, very small, this window is going to be pushed to the very end of inflation.
It's like a time-dependent mass. If you think about it.
Yeah. So I was confident that the back reaction effects could be neglected. Now, not anymore. Thank you. Let's take that into consideration. But so far, we've been ignoring the back reaction effects. And now, what we do at the moment, we are currently trying to compute the parameter space that's going to return 100% observed dark matter abundance. Now, without the approximation of H constant and C constant. So that we need to take into consideration the evolution of C, which is again only has meaningful value at the very end of inflation, and which is what I write on interesting feature that's really negligible for almost all of the inflation period. And the production only happens at the very end. And this feature is going to shift the energy spectrum of the dark matter towards higher momentum. You can compare those two plots here. So in this case here, I'm considering C to be a constant, 6.5, 5.5 or something. And the purple line is simply the vacuum. And we have production in momenta like K equals to H, for example, whilst here, and when I consider the evolution of C, to take this into consideration, the values of C here are much higher, 650, for example, and production is shifted towards higher in this case. This is one of the features that differ most from between low scale inflation and high scale inflation. And also here we can see the evolution of these modes in time. Let's see if I can explain this plot to you. So we have lower momenta here, and here reaching momentum, like k equals to h, and on top here we have momentum like k equals 10 times h. And the purple and red lines represent the consideration that C is constant. So essentially, C is going to be produced later on for higher momenta, earlier on was for lower momenta, and it's going to have this behavior. Here we have in the y-axis, we have the density field essentially. And meanwhile, for C equals to 65, all of the other lines are going to be essentially equal to the vacuum. There's no production in this case. And here I have considered C to be 650, and we see that for low momentum, I have no production. For momentum equals K equals H, I'm not sure if you will be able to see here, but there's a very small bump here at the very end. And this green line is easier to see, which is with K equals 10H. Then here we have actual production at the end of inflation. This production is exponential. So this is why the spectrum shifts towards higher momenta. We have more production of higher momenta modes. Now we need to integrate all of those spectra and calculate the energy density, considering the redshift of the momenta, etc., in order to find what is the dark matter abundance today, and to find the parameter space to see what goes on. So next steps are integrating this, finding parameter space, extending the analysis to other values of H, because so far I have only used 10 to the 7 GeV. I could also compute scalar Gaussianities for observational constraints. And of course, we can consider different potentials, because so far I have only considered the T1 model, T model with n equals to 1. Now, in light of new ACP constraint, we might be interested in searching for other alternatives. And now I'm going to include the back reactions again in the list. Oh, that's all I wanted to tell you.
Questions for Gustavo?
Well, ACP, like, do you know if ACP alone measures some mega imbalance at the end of this complete plan?
Omega,
Like, again, amount of plan.
don't remember.
The act, I believe they have chains available, we've made them public. It's not in the paper. So yeah, that's the value of omega matter that act measures is pushing the NS away from, so towards 1. And that's why that is mainly given by DESI at that point. And so that's why we are hesitating a little bit onto the.
But as you mentioned, I mean, the omega and the plan from the omega and the so like combining the two, it's a bit issue.
Yeah.
So from what I understand, combining this data with this is kind of problematic.
I believe it's because we are measuring, we are combining
Different
data from fundamentally different probes. That it's difficult for one scientist in the collaboration to understand the entire pipeline in the ACT collaboration, for example, but then to go and combine it and understand all the systematics associated with the DESI data, that is a new experiment, and the ACT data that's kind of taking DESI and making it apply strongly at the NS plane, that it's, I believe they don't have the authority or not, they don't have the authority. I think it's early for them to say. I would prefer to see a solid result from the ACT chains, combined with Planck. Because DESI is a DAO measurement, it's a completely different redshift, it's not CMB. There's a lot of interpretation issues with their data, not from the pipeline, but from the more theoretical priors. And so, yeah, I'm very interested in seeing Planck and ACT, and what do they do alone for the NS.
It's at least a questionable analysis to simply include the data from this.
Yeah, but I believe that in cosmology we are underestimating how intricate the analysis of all these probes by BAO scale that comes from several quasars, different types of galaxies, very different spectra. ACT is again a completely different type of probe. And if this was solving several years long, 1 decade year long experiment, I believe it's okay. But at this point, to combine them, we lose the sense of where are the main anchors coming from that are pulling together in a very, very solid, the NS and R determine a lot of the universe. And so if we're pulling one from here, from the BAO, one from the CMB, without knowing exactly what are the implications associated, then there needs to be a more cohesive interpretation. And so seeing ACT along with plan would be very, very interesting.
I agree.
So I got a bit confused now. So you do have some tensions between ACT and DESI.
Now, essentially, this is very important, very different from ACT. ACT,
No, it's like they're the same. So what the parameters are the same.
Oh, but they're measured, the probes, the cosmology probes are completely different.
Yeah.
And the systematic, so, yeah,
Why is
that's
it important?
interesting. I want to hear your point of view more, because I need to understand how serious this is. So can you say more?
No, just because the universe one doesn't matter how you observe the initial condition. Are just different ways of getting the initial condition. So I understand that you have these obligations or observations, but once you take it account, you can combine, or you don't take it account, you cannot do it.
Short answer to that, I don't know about that, but I definitely know that the Planck speed from again and the basic AO or basic full shape speed alone from again, you know, maybe. But
Okay,
yeah, they just give you Planck gives some again at 151 and BAO 29. So
Oh,
I think
okay.
okay, I didn't know.
the combined data are still maybe like because the errors we get from they see alone are large enough that there's no deep tension. But
Sorry, what do you mean with combining data? Because
Like,
they are
when-
intentional to combine.
like when you put together the posterior, the 1 sigma, 2 sigma controls combined in such a way that the final.
Why do it make sense? Why does it make sense?
I mean, it's just because they see alone without any other information is not so strong in constraint on again. Like you have to put something else, for example, Planck.
Sorry, how large is the patient?
It's within 2 sigma. Yeah, so it's not really attention, but they definitely like that's what is driving the preference for dynamic interchange. At the end of the day, CPM is referred to Lance DM in the BAO analysis just because the values of omega have different products. Like you take supernova, they want the best fit for omega is 0.35. You take BAO, the best fit Planck, the best fit Lance DM is 28, and then Planck is 31.
Yeah.
So you have 3 data sets that do not agree on alone individually on the value of again.
Yeah.
But when you combine the 3 likelihoods together with the fit of all the data together, you get a consistent transfer.
Yeah, it's really interesting. That's why I was wanting to hear your perspective, because I started also as a theorist, and then I went into these collaborations and I gained an understanding of what the systematics and uncertainties in producing the final result are. And when there are tensions, if you spend time in a collaboration, then you understand, hang on, before we draw combined constraints that will imply or modify our vision of the universe, we have to understand very well the systematics.
Yeah, I understand.
Particularly, yes, you already said that it's coming from the supernova, which is the hot topic of the last few years. But if I believe it in theory, sometimes that's why I was so interested. theory, we can have an idea that the universe is there and whatever probes we collect, we're gonna get the right measurement from those probes. So then when we have attention, as we've been starting to have recently, we have to be really very careful. Because if we get latched on to attention from the theory side, for the world community that will draw the theorists to work on attention, that may actually lay on some doubts that are coming from systematic uncertainties, be it either the team that is having a different method for fitting their data, or even uncertainties with the probe itself. And so the moment we're living right now in cosmology is really very crucial, because if we don't work out these tensions in time, it looks like the community is going to be coupled to the tensions. And when the theorists are working on tensions and funded by tensions in cosmology, then it will be very difficult to unpick the whole problem if it comes out that it's actually from data that problems the teams.
Yeah, I understand. My question here is only why you combine both data if they are intentional. This I don't understand very well.
Sorry, like,
Because
Oh.
you.
Oh, yeah.
Before are saying that act and definite are intention. For
yeah.
omega m. So you cannot combine the posteriors, even if you are just showing the marginalized over other parameters. Omega n is in the chains as well, right? At some point.
You can combine the posteriors, yeah, no, this is completely valid treatment. It's just that taking the conclusion very seriously from the theory side is very.
No, I'm talking about statistics. Why you can combine both chains? Why? Yeah, there are tension. So combine implication.
I would like I personally would present the contour in the two different cases we both buy, but that's not the big. So
Your question was why you cannot, or why you?
Why you can't combine? Why you make some sense? So any sense actually. That's my question.
The words that, why you?
Yeah, it's for the speaker actually.
Why can you combine?
Yeah, why can you?
Why is this
I
allowed?
don't understand this. You
Well,
want
why is this
to think
allowed?
that are intentions that are not.
For the dark energy survey, for instance, and when the analysis, when we have something that has tension with CMB,
Yeah.
we do not combine.
Yeah,
Yeah.
this for me, it's the nature of the.
Yeah, you can find it much more politically correct. Yes.
But then there should be a criteria to see whether something is intentional or not.
Yeah.
I think that 3 sigma is
There is.
criteria.
Oh, it's not just
Flexible as a.
there are other criteria, I forget. Remember, Walter?
this species versus.
The several, there was a whole paper in DS about criteria, like suspiciousness and such. So measures of tension.
I see.
It's not a unique measurement on
Yeah,
it's
yeah.
not a unique measure, different measures of.
We talk later because I don't know.
Okay, I didn't participate in the paper, but I can point this out to you.
Yeah, and DES has been around for years, and they've established your reputation and respect.
Thank you.
Your method for blinding, how many times do you blind things?
It's like, so it's very respected method with DESI. I mean, this is a very suspicious, the world is kind of surprised what's going on with this experiment, because they have with good result. The team is great, but they're having a lot of publicity, and no one could really understand why they're having this much publicity. So that's why when they become more, well, I can also speak because I was in DESI doing the forecasts, and so I know more or less the people who build the pipelines or the structures, and none of the main players are putting their name before the results. So I kind of, good, oh, yeah.
So not all the collaboration is signing the results? This is something.
Is this being recorded?
Oh, well, we should, okay, let's talk subscribe.
I could say, we've been talking to journalists for the last year or so, because the article that we had. And we've entered the era of anonymous source cosmology. I am talking to a reporter and I say, can I speak off the record? And then you can write it down. We know that the senior cosmologists are not signing the results. And the team that is actually the young postdocs, they're doing the very hard work. These are very solid. It's a very solid team that's gathering the catalogs. But then this theory interpretation is a free for all.
I believe he has a question.
Yeah, well, I was wondering, this production effective that matter, does it couple, of course, to the tensor modes, and that's why BSEP is giving you some, I would like to know how much space are you given in your vector production, like on the strength of the vector perturbation.
I'm not sure if I understand the question. Can you repeat?
Like naively, I would expect that if you have vector perturbations in with the inflow, the coupling between the scalar inflow and the vector modes will also introduce the production of some coupling between scalar and vector perturbation. So I'm expecting the vector field to source some scalar perturbations and the other way around.
Okay.
Sorry, vector perturbations and the other way around.
Okay.
So I would imagine in principle some gravitational wave production sourced by a vector field. And I was wondering how strong is this? Like I understand that the constraints can only come from this, which is still not so precise to experiment. But I'm wondering how much can you push the vector that matter production without creating an insane amount of gravitational waves.
We have those equations for production of gravitational waves, but we haven't computed that yet.
Consider vector perturbation at all.
How about tensor perturbations?
It's gonna be higher order.
Yeah, it could be like that. I just don't know. So
We haven't computed this yet.
Like scalar perturbations can also source tensor. This is the model that Paulo is working. Oops, was not allowed to say that.
right. It's an example down one of the scalar induced gravitational waves.
Scalar
But these
is
are right, and tensor perturbations sort of like second order scalar perturbations. But I don't know the details of your models.
Yeah, we have not delved into that, but
Yeah, that was my guess is that usually they should not matter at all. But since now you have a kind of stable vector production, then maybe you can source some very strong gravitational wave. That's why I'm like thinking that should be something that
they might. I'm not sure what to say.
Rodrigo has another.
So, yeah, just very simple question. Are you generating cold dark matter or warm dark matter?
It's called dark matter. It's called. Yes, it's not really very heavy.
Because you have some velocity.
The velocity.
Energy they connect part of the.
But we are considering the momentum of the dark matter modes to be much smaller than mass. So they're not relativistic. Yeah.
They are relativistic in the beginning.
At the beginning.
That's spectral, the redshift. So eventually they will become relativistic.
Sorry, in the initial conditions.
No, initially the spectrum, they are actually relativistic. But then when you redshift the physical momentum until at some point they become relativistic. It's actually to calculate the final spectrum dark matter density, to redshift the spectrum. So that you have some initial spectrum So I think initially all of them are relativistic, but then the momentum rate shift should eventually.
Because it reduced at the beginning of inflation, so the mass is comparable to the hub, right? So there was this in the beginning and then first, as the universe moves down, it evolves.
Any other questions?
If we have time, I have a question, but I think.
It's all around the world.
So maybe it's naive and maybe stupid, or maybe I didn't understand the thing, but let's try. So your dark matter it's a field. Does it get a non-zero there or not at the beginning of the just during inflation?
I don't know.
No.
I don't know.
Okay. Because you are saying it's so there's a vibration between the inflaton and the dark matter. So this vibration part occurs because one of you gets better. So it's not that. Don't know if that
The energy contribute to that.
it contributes, but like instead of having an electric field in
There's a background value for the field.
Yeah,
So
but
we
yeah,
should act like a
yeah, I think it's like that. Yeah, right. You think about it.
It's a legal line violation.
yes, so because
He has a term of E dot P.
yeah, exactly. So
Great over
Average.
average.
With the right.
It's not the ones.
Yeah, that's the term E dot P.
yeah.
Sourcing the vector, sorry, the scalar rotation. Maybe also the vector.
See the vectors.
Yeah, oh, there's no, it's only sourcing the scale.
So yes, there is no loss violation. Why?
I don't know.
Because you have a magnetic field and magnetic field in some directions. So that's correct. To make, makes no violation.
I don't know.
You don't have the other.
Yeah, then the
There is
average,
no further
the
direction.
average might cancel, or maybe not. Because you are saying there is no vibration, you find it's invisible. But so I was expecting that it's because your E times B is small or zero reason.
It is from the previous computations, which assumed that H and C are constant, though the source term was really negligible when compared to the values of H and V. So it's almost the same as considering it's zero, the E times B.
Small.
The real dynamics come from the master and the product that at least on the ground dynamics.
Back reaction should. It would be interesting to see what about it. Okay. So any further questions? So that's then Gustavo, now the speaker. You can stay here and continue discussions until 5 or 6, whatever. And also, if you're interested in DESI results, we're going to have a talk by Marina next Friday, so we come today and Institute.
Okay.
Or we're more than welcome to.
I want to hear your talk
Next
next
Friday.
Friday.
I think it's next Friday, yes. We're still
Yes.
deciding the time.
Here, Brazil.
No, at the Barra Funda.
Okay.
I have to. But,
Even easier,
sorry?
even better.
Even better because you're there, right?
Easier to reach us out for.
Good.
Thank
So,
you.
so there, if you don't know this, there's spaces here, we can stay.
Yeah.